So, good day to every one of you, no? Ang next na i-discuss naman natin is about earthquake loads. Katulad ko, kay wind loads, hindi ko na to ipe-present by calculation. So, more on mga philosophies na lang tayo. So, introduction na lang tayo for earthquake loads. Kasi, most likely, meron naman na kayong earthquake engineering pagkatapos nyo mag-structural theory or pag fourth year na kayo or whatever year level na. Okay? So, yun yung detail calculation doon. So, for the meantime, introduction muna tayo regarding sa earthquake loads. So, sige. So, what is an earthquake load? So, dito, an earthquake is a sudden undulation of a portion of the Earth's surface, no? So, alam naman natin na ang earthquake is bigla ang paggalaw ng Earth's surface, no? So, although the ground surface glass moves in both horizontal and vertical direction during an earthquake, the magnitude of the vertical component of the ground motion is usually small and does not have a significant effect on most structure. It is the horizontal component of the ground motion that causes structural damage that must be considered in the design of the structure located in earthquake-prone areas. So, ang ibig sabihin nito, class, no, yung lindol, may dalawang component, pwedeng vertical ang paggalaw niya or horizontal. Kaya lang, usually, kapag vertical, hindi siya masyadong delikado. So, halos nineneglect na lang natin yan sa design process. Ang mas kino-consider natin dito is the horizontal motion of the soil. Okay? So, yun. Again, during an earthquake, as the foundation of the structure moves with the ground, the above ground portion of the structure, so because of the inertia of the mass, resists the motion. So therefore, thereby causing the structure to vibrate in the horizontal direction. This vibration produces horizontal shear force in the structure. For an accurate prediction of the stresses that may develop in the structure in the case of an earthquake, a dynamic analysis considering the mass and stiffness characteristic of the structure must be performed. However, for low to medium rise rectangular buildings, most codes employ equivalent static force to design for earthquake resistance. In its empirical approach, the dynamic effect of the earthquake is approximated by set of lateral or horizontal forces applied to the structure, and static analysis is performed to evaluate stresses in the structure. So, anong ibig sabihin nun? Sa ating code kasi class, may tatlong methods ng pag-compute ng earthquake loads, no? So, there are three methods. So, yung una is the simplified static method, pero bihira yung gamitin kasi sobrang simple. So, yung pangalawa naman is the static method. So, static method. And yung pangatlo is the dynamic method. Sa kanilang tatlo, ang pinaka-accurate talaga is the dynamic method. However, syempre, since accurate din siya, ang complicated din ng computation niya to the point na computers na ang ginagamit natin. So, computer software. So, kung low to medium story lang naman, low to medium rise building din lang naman daw ang ide-design nyo, so, kung ganun din daw, what if ang gamitin nyo na lang daw according dito ay static method. So, ang static method is just an approximation to the dynamic method, pero accurate siya sa mga low-rise or mid-rise na structure provided na rectangular. So, maganda na rin approximation ang static method kasi kahit papaano, simple yung solution doon. I think sa earthquake engineering nyo, madidiscuss nyo class ang static method. Okay? So, next. So, ito yan, no? So, as the ground moves, syempre, magse-sway ang ating structure. Okay, so may swaying yan na magaganap. So, next tayo, kailangan natin i-discuss class kung anong ibig sabihin ng resonance. So, what is resonance? Resonance is the tendency of the system to oscillate with a greater amplitude at some frequency than the others. All buildings have a natural period or resonance, which is the number of seconds it takes for the building to naturally vibrate back and forth. The ground also has a specific resonant frequency. Hard bedrock has a higher frequency, softer sediments, no? So, if the period of ground motion matches the natural resonance of a building, So it will undergo the largest oscillation possible and suffer the greatest damage. So usually, high-rise structures have low resonance frequency while low-rise structures have high resonance frequency. So, pag sinabi nating class, resonance, yun yung tendency ng structure na mag-sway nga or gumalaw. So, with greater amplitude or displacement at some frequency. So, halimbawa, naka-specific range lang to. So, halimbawa, yung ating structure is mag-sway lang siya between 4 to 10 Hz. No? Ganun lang. So, yun. 4 to 10 Hz lang siya. So, kapag yung frequency ng paggalaw ng lupa is less than 4 Hz, hindi siya gagalaw. Kung ang frequency is greater than 10 Hz, so hindi rin siya gagalaw, no? Pero kapag doon sumakto sa range na yon na 4 to 10 Hz, so magsesway yung building natin. So hindi nangangahulugan na kapag mabilis yung frequency, delikado na. So kasi ang kada building, meron siyang kanya-kanyang resonant frequency or natural period or resonance nga. So usually, tandaan nyo itong nasa baba, kapag ang structure natin ay high-rise, so low resonance frequency lang, mabagal lang yung paggalaw ng earthquake waves, no? So, o yung paggalaw ng lupa, mabagal lang. Pero, kapag mga low-rise structure, meron siyang high resonance frequency. So, therefore, ang ibig sabihin ng class, kung lumindol man, tapos mabagal yung paggalaw class ng wave, ang delikado ay mga high-rise structure. Uulitin ko, kung lumindol man, tapos yung frequency natin ay mababa, high-rise structure ang most likely masisira. Pero, kung lumindol, tapos mabilis yung frequency, normally, yung mga low-rise ang masisira. Okay? So, para mas maintindihan nyo yung konsepto ng resonance, I strongly suggest na panoorin nyo itong mga videos na to. Pero sige, ipe-play ko na dito sa video ito class yung isa, itong number 1 na video. Okay? So, nasaan na siya? Ito. So, this is the resonance vibration test. And ipapakita niya dito class kung paano gagalaw ang mga structure depende sa frequency ng paggalaw. So, wait, i-pause ko muna siya. Ang tawag natin dito is a shaking table. Ginagamit natin to para i-simulate ang structure under earthquake loads. So, meron tayo ditong high-rise structure, then meron tayong mid-rise structure, and meron tayong low-rise structure. So, sige. So, nag-i-increase gradually class ang frequency ng paggalaw, no? From mabagal na paggalaw, bibilis na rin yan ng bibilis, no? So, yan, for low, frequency. Tingnan mo muna. So, unti-unti, bumibilis na yung ating, shaking table natin, no? Ayan, bumibilis na siya hanggang sa... Ayun, no? Kung mapapansin nyo, ang unang nagre-resonate o ang gumagalaw ay low-rise building. So, kasi nga, medyo mabagal pa rin naman yung ating frequency. So, yun. At low frequency, gumagalaw ang mga high-rise building. So, ilang hertz kaya to, no? So, while yung mid-rise, tapos yung low-rise, is steady pa sila sa low-rise or sa low frequency. Ayun, no? So, at 4 Hz, grabe na yung paggalaw nitong high-rise building. So, to remember, itong table natin, yung frequency yan, ay nag-i-increase yan, no? Tingnan nyo na lang yung paggalaw. Nag-i-increase yan ng nag-i-increase. Ayan, no? So, yun, medyo bumabagal na ang paggalaw class. So, pero bumibilis yung table, So, therefore, itong frequency na to, mabilis na to class to the point na, no, ang gumagalaw naman na o ang nagre-resonate na class ay ang mga mid-rise building. So, kasulad ng sinabi ko, pag low frequency, ito ang gagalaw. Pag, gitna lang yung frequency, mid-rise yung gumagalaw. So, saktuhan lang sa frequency. And in this case, 6.35 Hz siya. So, mas malaki yung frequency ni mid-rise structure. yun, bumibilis pa rin yung ating cable, no? Bumibilis ang frequency niyan. So, di ba, no? Mabilis ng frequency pero steady na class yung ating high-rise building. Kasi nga, hindi naman yan yung saktong frequency. So, pabilis ng pabilis sa pagkakataong ito, low-rise naman na ang medyo delikado ngayon. So, ayan, no? Steady na itong low-rise, oh. Ay, steady na itong high-rise. Medyo steady na rin itong mid-rise. Pero si low-rise, ayun na siya, nagre-resonate na siya. So, dito, kapag mabilis na ang frequency niya. And yun is 11.35 Hz. So, grabe ang resonance niya doon. Pero itong high-rise saka mid-rise is hindi na siya ano, no? So, steady na siya. Ayan. So, tapos na tayo. So, explain ko lang yung ibig sabihin nun, no? Usually, at high-rise structure, have low resonant frequency, while low-rise structure have high resonant frequency. Okay. So, next tayo. Itong remaining 3 videos, nandito lang naman yun, class. Ito lang naman yun. So, ina-explain lang niya itong assembly for high-rise, mid-rise, and low-rise. So, ganito rin.
A prolonged wind swung the bridge on the right at its natural frequency until it exceeded its structural integrity and tore apart.
Ulitin ko, no?
Energy. A prolonged buildings during earthquakes. We will look at other resonance systems. To understand the resonance of buildings during earthquakes, we will look at other resonance systems. The natural frequency of a swing makes it easy to maintain the motion.
Kung mapapansin nyo, itong bridge dito na video sa kanan, akala mo, no, animation lang yung bridge na yan na gumagalaw. Pero totoo yan, nangyari talaga to.
A prolonged wind swung the bridge on the right at its natural frequency until it exceeded its structural integrity and tore apart. The frequency...
So, kayo na lang, bahala nun, class, na manood. So, ganon din dito. This is a TED-Ed video. Maganda din siya.
Earthquakes have always been a terrifying phenomenon, and they've become more deadly as our cities have grown, with collapsing buildings posing one of the largest risks. Why do buildings collapse in an earthquake, and how can it be prevented? If you've watched a lot of disaster films, you might have the idea that building collapse is caused directly by the ground beneath them shaking violently, or even splitting apart.
So, kayo na lang magpatuloy nito, class, no, na manood, no. Okay, ibibigay ko naman yung link sa description. Next tayo, next slide. So, design and technologies tayo to resist or reduce the lateral loads. So, una, diagonal bracing. So, sometimes, class, placing a diagonal bracing in the structure helps to resist the lateral loads acting on the structure. So, yun, napakasimple lang nitong design, class, diagonal bracing. Tapos, because of those bracing, class, nagiging mas simple yung, or nagiging mas rigid yung structure natin. To understand the effect of diagonal bracing, ito yung YouTube video, i-play natin siya. So, kung mapapansin nyo, meron tayong building simulation na walang bracing dito, class, pero itong isa naman ay merong bracing. So, panoorin natin kung anong mangyayari. So yun, nakita nyo agad class na yung structure natin, dito ko no, nakita nyo na yung structure na may bracing is bihira yung oscillation niya as compared sa structure na walang bracing. So yun, by simply providing a diagonal bracing, nagiging mas matibay yung structure natin, di ba? So yun, at least. On the other hand, another thing is damper. So seismic dampers permits the structure to resist severe inputs energy and reduce harmful deflection, forces, and acceleration to structure and occupants. There are several types of seismic dampers, namely viscous damper, friction damper, yielding damper, magnetic damper, and tuned mass damper. So by the way, may tuned mass damper din naman tayo mamayang pag-uusapan. Pero, itong damper na tinutukoy nito sa video na to class is a viscous damper. So, parang naglagay siya ng shaft sa structure. So, medyo mahal to. Normally, ina-apply ito sa mga high-rise structure. So, ito siya. So, this is a damper class, no? Okay, no? So, this is a viscous damper. So, ina-apply yan sa mga high-rise structure kasi para siyang shaft. So, yung shaft baga, di ba? Yun yung nag-a-absorb ng energy kapag gumalaw itong structure. So, para makita nyo kung gaano ka-effective itong viscous damper natin. So, this building has no damper, while this one, meron tayong nilagay na damper. So, play ko. So, ayun class, nakita nyo na kapag may damper, mas matibay siya. No? Mas bihira yung paggalaw ng structure. So, yung pangatlo ay base isolation. So, a base isolation is a state-of-the-art method in which the structure or the superstructure is separated from the base or the foundation or substructure by introducing a suspension system between the base and the main structure. So, ang base isolation, ginagamit natin to para ang ginawa, literal class na pinaghiwalay yung building nyo saka yung footing or yung base. So, from the title itself class, nagsasuggest ito na pinaghiwalay natin yung base saka yung structure. So, not totaling nakahiwalay siya. Ang gusto lang naman nitong i-point out class ay kapag may lindol, magmumove ng onte yung ating structure from the foundation. So, para mas maintindihan nyo yung concept ng base isolation, so may dalawa tayong YouTube video. Ang ipe-play ko lang is itong isa class. So, this one. So, kung mapapansin nyo, itong isa na structure, napaka-rigid niya, wala siyang base isolation. So, on the other hand, dito naman, no, may base isolation na nasa baba. And tingnan natin kung gaano ka-effective ang base isolation. So, yan, lilindol. Kung mapapansin nyo, dito sa swimming pool, sa taas, mas steady yung swimming pool doon sa may base isolation as compared sa wala. So, bakit? Kasi, literal na, humihiwalay, may tendency humiwalay yung ating, base sa structure. So, ito yung walang base isolation. Tingnan nyo. Ito naman yung may base isolation. Parang wala lang. And, yan. Ito yung nangyayari sa base isolation natin. So, ayun class, I hope na-gets nyo yung ibig sabihin nitong base isolation, no? Napaka-powerful nitong video na to. So, madali lang naman mag-gets yung function niya, di ba? And ito, yung isa, this is a base isolation as well. Kaya lang, ibibigay ko na lang to sa inyo para panoorin nyo. Okay, so kayo na lang bahala nito. So lastly, as I said earlier, tuned mass damper. So a tuned mass damper, also known as the harmonic absorber or seismic damper, is a device mounted in the structure to reduce the amplitude of the mechanical vibrations. Their application can prevent discomfort, damage, or outright structural failure. They are frequently used in the power transmission, automobiles, and buildings. So, sa mga buildings, pag sinabi natin tuned mass damper, so mabigat to na damper. Pero yun nga, para mas magets nyo, I prepare or I paste dalawang link sa YouTube para i-play nyo na lang. So, sige, meron ako dito. This is a basic illustration of a tuned mass damper class.
Like a pendulum. And
So ito, yung nag-aak na parang pendulum class, yan mismo yung tuned mass damper ng structure. Dito, itong model ng structure, wala siyang tuned mass damper. Okay, so tingnan natin kung anong magiging
when
effect.
we add that, we actually make the building better because now it looks less than before.
So, in terms of deformation, mas malaki tong pag-deform ng may mass damper. Ay, nang walang mass damper. So, yun yung effect ng tuned mass damper. Ina-absorb niya yung
But
energy.
it also has to be like the right one because if you, for example, make it longer, it probably doesn't work as well because it really moves more now. So you have to like find the right
frequency.
Okay. So, end natin. So, yun yung konsepto ng tuned mass damper class. So, ito rin, tuned mass damper to. Yun kasi fixed siya, so hindi siya kinoconsider na tuned mass damper. Pero kapag gumagalaw, ayun. Wag na natin siya masyadong May isa pa akong video for tuned mass damper. Ito, pambata siya. So, panoorin na lang natin kung gaano nga ka-effective ang tuned mass damper.
When you're testing a building to see if it will withstand an earthquake, you're going to need a shake table. I'll show you how to do it. It's coming right up. Hi, my name is Justin. Today, I want to show you how to make a simple shake table. This will be helpful when you're testing a building that you've designed to see how earthquake resistant it is. You'll need 2 wooden dowels that are 3 feet long, 2 30-inch long pieces of PVC, 2 24-inch long pieces of PVC, 4 elbow pieces of PVC, 4 eye bolts, 8 nuts, 4 bolts, 4 elastics, and a wooden board that's 24-inch by 24-inch. Let's put it together. Drill 2 holes in the 24-inch long PVC pieces. All my PVC pipe is 3/4 inch.
So, construction lang naman to ng shake table, no? Doon na ako sa mas importanteng video, yung ito.
Will now move and shake freely. To see my science project where I make earthquake resistant.
So, yun ay pag-build pala to ng shake table. So, actually, nandito siya, class.
What
Pasensya
the
na.
natural disasters are and how people die.
So, hintayin muna natin
Used by
mag-loading.
architects and research, I found out that it's not earthquakes that kill.
Wait lang.
It's an earthquake! Just kidding. Today, I'll is how to make an earthquake-proof building. Hi, my name is Justin. It's a heavy weight that. So let's start with the tuned mass damper. We got this idea from Taipei 101 in Taiwan. The tuned mass damper is often used in tall structures. It's a heavy weight that's suspended on the inside of the building to help minimize the movement and vibration. It's time to make my buildings and test it out. I used pieces from my Engino construction kit to make two identical structures that are 3 stories high. I built my tune mass damper putting 12 washers on the eye bolt and screwing the nut on. I built an extra part on the top of this building so I could suspend the tune mass damper on it. Now it's time to test it on the shake table. See how much of a big difference there is? The building with the tune mass damper stays pretty steady and doesn't wobble or bend too much. Check out the building without the tune mass damper. It swung like crazy. This seems to work because when the building sways one direction, the tune mass damper moves in the opposite direction and pulls it back from swaying too far. Some of the variables that would change the outcome of this experiment is the height of the tune mass damper. If it's too high, it will not make a difference, and if it's too low, it will swing too much. Also, the height of the building makes a difference, and the weight for the tune mass damper. If it's too heavy, it might crush the building, and if it's too light, it won't make a difference. So, it looks like the tune mass damper is very effective at minimizing the movement and vibration in a tall building. Now, on...
So, yaan ko na doon. So, at least nakita nyo yung effect ng ating tuned mass damper sa building. No? So, yun. Dito ko na tatapusin yung formal lecture natin sa earthquake and yun, earthquake loads. So, actually, ipagpatuloy ko na rin for other loads. So, ano lang naman to, hydrostatic and soil pressure and thermal loads. So, yun. Thank you. I-end ko na siya dito. And I hope may nagets kayo sa ating discussion.